we have seen that we need to generate a train of pulses with variable duty ratio, and the variation of duty ratio is also sinusoid. That is what we need. But what do you mean by pulse? A pulse will have one value for a given interval and some other value for another interval, and it goes on. How can these abrupt change in values happen? These abrupt changes in values can happen if we compare two things, two functions, two signals. If one signal is greater than the other, then the condition is true, pulse will have one value. When the condition fails, the pulse will have another value and it goes on. So here for our pulse generation, we are considering two signals or two functions. What are those? One function is drawn in blue color, that is I am calling it as CT. Okay, CT, and the other function is drawn in green color, that is MA. And what is CT? How does CT look like? CT is a triangular wave, a triangular function. It starts at plus Vp, goes to minus Vp and comes back to plus Vp, and all this happens within an interval of Ts. And over this interval of Ts, how does MA look like? MA is a constant value. MA has a constant value over this Ts. And what is the logic for pulse generation? Simple. If MA is greater than CT, then S1 on, S4 off. If MA is less than CT, S1 off, of course S4 on. That is the logic. So if you follow this logic, when S4 is on, what is VAO? VAO, the voltage VAO will be minus VDC by 2. That is in the very first interval. And then MA becomes greater than CT. So S1 becomes on and VAO becomes equal to plus VDC by 2. And it continues to be so till this interval, this instant. And at that instant, again MA becomes less than CT, or CT is increasing, so CT becomes more than MA. So our condition fails. S4 becomes on and S1 becomes off. So when S4 is on, VAO is minus VDC by 2. So by comparing two signals MA and CT, we can generate a pulse as shown here in red color. What is the width of the pulse? Because we have been interested in the width of the pulse. So width means in terms of time. Height is known because the pulse is always varying between minus VDC by 2 and plus VDC by 2. But what are the relative intervals of minus VDC by 2 and plus VDC by 2 is what we are interested in. So we look at the two triangles ABC and DEC. Then by similar triangles we can write that AB by DE is equal to BC by EC, and which is equal to 2VP by VP plus MA. We are just considering the magnitudes, is equal to TS by 2 is BC and DTS by 2 is EC. We are defining the interval in which S1 is on as DTS. So with that, the value of D will be 1 by 2 plus 1 by 2 MA by VP. Let us look at the relation between D and MA for a given VP. If MA is equal to 0, D is 0.5. And if MA is greater than 0, D is greater than 0.5. And if MA is less than 0, D is less than 0.5. We have been thinking about generating pulses of duty 0.5 going all the way up to 1, then again coming back to 0.5, then going to 0, again going back to 0.5. That is what we have been thinking. So that can be generated by comparing a function MA with CT. and the peak value of Ct is Vp, the absolute peak. So for a given Vp, let us look at the relation between D and Ma. When Ma is equal to 0, D is equal to 0.5. When Ma is greater than 0, D is greater than 0.5, and when Ma is less than 0, D is less than 0.5. And when Ma becomes equal to Vp, D is equal to 1, and when Ma is minus Vp, D is equal to 0. What do we understand from this? If we want to generate pulses of variable duty cycle and the variation of duty cycle is sinusoid, for example, it goes from 0.5 and it goes all the way up to 1 and comes back to 0.5 and becomes 0, then again reaches 0.5 back within one interval of t1, for example. Because this is what is needed to generate an average voltage which is sinusoid. You need a duty cycle which goes around 0.5 but varies as a sinusoid, is what you need to generate a sinusoidal average voltage VAO. And these kind of pulses with this sinusoidally varying duty ratio can be generated by comparing a signal or a function Ma against Ct. And what is Ma? Ma will look like this. Ma is a sinusoid having 0 average value, and Ma goes all the way up to Vp. Why? When Ma is equal to Vp, D is equal to 1, and when Ma is equal to minus Vp, D is equal to 0. So if you compare a sinusoidal function with a triangular function, if you compare a sinusoidal wave with a triangular wave, following the logic, when sine is greater than triangle, switch S1 is on. When sine is less than triangle, switch S4 is on. Or when sine is greater than triangle, top switch is on. When sine is less than triangle, bottom switch is on. If you follow this logic and generate pulses, these train of pulses will have variable duty ratio, and the variation of duty ratio is a sinusoid. Remember, what is the periodicity of this duty cycle variation? The periodicity here is T1, and Ts is much smaller than T1. Because Ts is much smaller than T1, even though we are saying that D is a sinusoidal function or Ma is a sinusoidal function, in that small interval the sinusoidal function can be assumed to be constant. That is why we have drawn D and Ma like a stepped sine wave, So we are generating pulses of variable duty cycle, or the width of these pulses is being modulated. And how is this being modulated? It is being modulated using two functions, sinusoidal function and a triangular function, and that is why this method of pulse generation is known as sine triangle pulse width modulation. And what is the average value of VAO over Ts? We have already seen that it is equal to 2D minus 1 times VDC by 2, and if you insert the relation between D and Ma here, it will be simply equal to Ma by Vp into VDC by 2. It's a very interesting result. We have already stated that the average value of VAO over Ts is same as the fundamental component of VAO, that is VAO1. We have to remember the fact that we are looking at a very small interval Ts. So a continuous sinusoidal function, because fundamental component will be sinusoidal of any function and it's a continuous signal. So that continuous signal can be approximated by a constant over a small interval. That is why we are saying VAO average over Ts is equal to VAO1. Means we assume that VAO1 is constant over that small interval. and VAO1 or the fundamental component of VAO is represented as VAO1 peak sin omega t as shown here. And from this relation, VAO1 is proportional to MA. For a given VDC and V peak, VAO1 or VAO average over TS is proportional to MA. That means if you want VAO average to be sinusoidal, which is equal to the fundamental component, MA also has to be sinusoidal, and that is what is represented here. MA is equal to Vm sin omega t. So the fundamental component of VAO is proportional to MA. Or if you want a particular fundamental component to be generated with a given VDC, you adjust this ratio Vm by V peak such that you get the desired peak value of the fundamental component, and you also adjust this omega so that you get the required omega. So for a given DC input voltage VDC, we now know that an AC voltage of desirable fundamental component, magnitude and frequency can be generated by comparing a sinusoidal wave against a triangular wave, and the peak value of the sinusoid can be varied as per the required peak value of the fundamental component, and the frequency of the sinusoid can be varied as per the required fundamental frequency. And this sinusoidal wave is popularly known as modulating function, because this is the function which is used to modulate the width of the pulses. And the other function with which this modulating function is being compared, or that which is the triangular wave here, is known as the carrier wave or carrier function. So we have a sinusoidal modulating function and a triangular carrier function. Both are being compared against each other to generate a train of pulses which have sinusoidally varying duty cycle and which produce a desired fundamental component, and the magnitude of the fundamental component and frequency are controllable as mentioned earlier. We can do a similar thing with the leg B or switches S3, S2. So whenever S1 is on, we can simply keep S2 also on, and whenever S4 is on, we can keep S3 on. So that will result in VBO average being equal to minus VAO average, negative of VAO average, because it's just the inverse of VAO. So that is equal to minus MA by VP into VDC by 2. And now our load voltage is the voltage across A and B, that is VAB. The average value of VAB over TS will be VAO average minus VBO average, that is MA by VP into VDC. And this average value is also the fundamental component of VAB, denoted by VAB1. And since MA is a sinusoid Vm sin omega t, we can express the fundamental component of VAB as VAB1 is equal to VDC times Vm by V peak into sin omega t. So this Vm by V peak, that is the ratio of peak value of modulating function to the peak value of carrier function. Here it is the peak value of sine wave, the ratio of peak value of sine wave to the peak value of triangular wave. Vm by V peak is popularly known as modulation index. And what does it represent? It represents the peak fundamental voltage that you get, because VDC is fixed. Let us say VDC is 100 volts. If we want our peak of the fundamental component to be 100 volts, we should use a sinusoidal modulating signal whose peak value is same as the peak value of triangular wave. That is how you can control the amplitude of the fundamental component. And of course, the frequency can be varied by simply varying the frequency of MA, the modulating signal. This method of PWM is known as sine triangle PWM, as stated earlier. And this is again a specific case of sine triangle PWM. It is bipolar sine triangle PWM. Why is it bipolar? Because with this method of switching both legs A and B, we are resulting in an output voltage VAB, load voltage VAB, which has both polarities in any given carrier cycle. So VAB is plus VDC and minus VDC in any given triangular cycle. So this method of switching is known as bipolar sine triangle PWM because of that reason.